Hybridization lecture number 9. So we're going to continue this process of looking at structures and trying to explain the shape and those presence of electrons, and relate where they are in the three-dimensional shapes that we've talked about in the Lewis structures compared to where they were theoretically in the atomic orbitals. And this process is called hybridization. So if we look at the ammonia molecule, right, the NH3, if we look at the electron configuration for nitrogen, we have that a 1s2, 2s2, 2p3. So there's 3 unoccupied places within the nitrogen. Right? So if this nitrogen is then binding to 3 hydrogens, that gives a place for that 1s electron from the hydrogen to fill. So each one of the 3 hydrogens is going to donate an electron to this, or share an electron with the nitrogen to completely fill this p orbital of the nitrogen. Right? And then we can, in theory, think about, there's a lone pair also in the Lewis structure of ammonia. That lone pair we can sort of equilibrate to these 2s electrons that are sort of together, that aren't being shared. Right? If we remember the shapes of the p orbitals, those different p atomic orbitals are 90 degrees from each other. So we would predict, using our atomic energy model, or atomic orbital model, that ammonia should have a molecular geometry where the hydrogen bond angle is 90 degrees. But if you remember, our Lewis structure said that has a tetrahedral arrangement, so the bond angle is about 109, but the lone pair takes up more space, so those are compressed, so it's about 107. And in actuality, if we measure the bond angles, we see that it's 107.3. Right, so there's this difference. One model is predicting a bond angle of 90 degrees, and in actuality, the bond angle is 107. Right? That's a big difference. So we have to come up a way of adapting our model to explain what we're actually seeing within the molecule. And what we've come up with is 2 different methods. One we're going to talk about today is hybridization. In hybridization, we're saying, okay, well, maybe it's not these individual distinct atomic orbitals anymore. Maybe we mix them together. Remember, they're wave functions, so they're waves. Maybe we can constructively add them together to get a new set of waves, new set of possibilities, or new set of orbitals. And that's what we have in this hybridization. We take these atomic orbitals that are involved, the s and the 3 p's, mix them together in this hybridization process, and get out a new set of orbitals that have a different shape and are arranged differently. And mathematically, we can see that when we can mix those 3 in such a way that the result gives us a bond angle of about 109.5. Right? So this explains the bond angles that we're observing. If we look at for methane, we see that all of those are occurring. Right? But they're 4 distinct different orbitals. They have some characteristics of their original orbitals that were mixed together. There's some s character and some p character, but they are different. Right? So in this hybridization, we're mixing 2 or more atomic orbitals to form a new set of orbitals. The key is that we have to mix 2 non-equivalent orbitals. We have to mix at least an s with a p. Right? We can mix more than that, but that's the minimum we have. And these new resulting orbitals have a different shape than the original orbitals. The number of hybrid orbitals that we get out is going to be equal to the number of pure atomic orbitals that we put in. So if we put in 2 atomic orbitals, the s and the p, we're going to get out 2 new orbitals. If we put in 4, the s, and all 3 of the p's, we're going to get out 4 new hybrid orbitals. Right? And it's these hybrid orbitals that are going to allow for the bonding. So we can get a covalent bond is going to be a direct overlap of 2 hybrid orbitals, or the hybrid orbital with one of those original atomic orbitals. Those are the 2 possibilities that we get. It's those interactions that's going to lead to a bond. And we can predict the hybridization around a central atom by counting the places we need to put electrons. Since we know how many, once we know that, we know how many hybrid orbitals we need to get out, we can then predict how many, or determine how many atomic orbitals we need to put in. So for example, if we have 2 places where we have electrons around the central atom, 2 places of bonding, or a lone pair in a bond, then we were going to see that we need 2 places, 2 atomic orbitals, the s and the p. If we have 3 places where we need to put electrons around the central atom, that's going to be 3 atomic orbitals, the s, and 2 of the p's. So it's sp2 hybridized. If we have 4, as we've seen, the s and all 3 of the p's give us 4 sp3 hybrid orbitals. If we have 5 electrons, or 5 places where we have electrons around the central atom, is going to violate the octet rule. Remember, we said we could violate the octet rule because of the presence of d orbitals, occupied or unoccupied. The ability to have these d orbitals allow us to violate the octet rule. And we can see this is confirmed by this hybridization. We're mixing in 5, we're mixing the s, all 3 of the p's, and then 1 of the d's. 6, an s, all 3 of the p's, and now 2 d's. And we can continue this trend, although we don't normally see stuff beyond sp3d2. So to predict hybridization, we are going to draw the Lewis structure, make sure it's the most appropriate Lewis structure, count the places where we have electrons around the central atom. That number is going to tell us how many atomic orbitals we mix together, start with the s, and move up from there. Right? So it's, again, all based on these Lewis structures. So when we talk about these places of electron located, that will either be a single, double, or triple bond. That we all count all of those conditions as one location. And that gives rise to this different types of bonding. We said that the bonding can occur if we have a direct overlap of these hybrid orbitals. Right? If we look at the Lewis structure for ethylene, CH or H2C2 C2H4, where we have carbons bound together and then 2 hydrogens. In order to get that Lewis structure, we're going to see we have a double bond, which means we have 3 areas around each one of those carbons where we have to put electrons. So this is going to have sp2 hybridization. Right? So we're going to get one bond that overlaps from these 2 hybrid orbitals, right? The sp2 of one carbon with the sp2 of another carbon. Right? That is going to form, it's going to be a direct overlap. That's going to be what we call a sigma bond. But both of those carbons still have a remaining unhybridized p orbital. So if those hybrid orbitals are arranged in this way, we have an unhybridized p orbital sticking up here. And we can see that those can interact in a sideways fashion, above and below the plane of bonding, and give us the second bond, or the third bond, depending on how many we need. Right? That indirect overlap is what we call a pi bond. It has the plane of the bonding above and below our thing. Right? So these direct overlaps are sigma bonds. The indirect overlap are between the 2 nuclei, sigma, not in between the 2 nuclei, pi. Well, we can break it down this way, that a single bond is a sigma bond, a double bond contains a sigma, the direct overlap, and this indirect overlap, the pi bond. A triple bond then would have the direct overlap and then 2 indirect overlaps, or 1 sigma and 2 pi. So looking at this, we can then calculate or determine how many pi's and sigmas we have. So in this molecule, we will see that there are 6 single bonds and 1 double bond, so that's a total of 7 sigma bonds. The double bond will give us 1 pi bond. So if we have these pi bonds that are arranged in sort of a symmetric way, or through resonance, we can put places where we have this sigma bond or this pi bond, double bond, it can move. Right? We're going to have a process we call delocalization. Right? So these electrons now, especially through hybridization, aren't stuck between two atoms. They can move around, right? Which is going to allow those electrons to move around the molecules and not be localized between any two atoms. They're delocalized, right? Which is going to allow us to extend these molecules through resonance of these electrons as here, right? So we can see benzene's a prime example of that, where those double bonds sort of are staggered and there's a resonance structure between them. So in actuality, those double bonds can move around and we have a delocalized environment.
Dad, I didn't do it.